Hi all. In today's session, we are going to learn about image classification using Keras. So image classification is one of the most happening areas in the field of data science. The applications range from using our fingerprints or face to unlock mobiles or identify vehicles at traffic lights, for example, for their speeding or any suspicious vehicle, etc. So it uses deep learning. So today, let's see how we are going to make use of Keras in the backend and build a neural network to perform a classification. So before actually jumping into the actual problem, today we'll learn how to directly import a data set from a given Kaggle URL. So let's quickly show you guys what exactly is the data set we're going to deal with. So we're going to deal with a Chessman image dataset. So this is the URL which will be shared as a part of this exercise. And this is the data. It comprises of 6 directories within the chess folder. Essentially, each directory corresponds to one of the chess pieces, like king, queen, rook, bishop, etc. So the first step is install the Kaggle library. And once it is installed, the next step is to provide the API JSON file into this particular Google Colab environment. So let me quickly show where it is present. Quickly jump into your account details, and over there under the API, there's something called the create new API token. The moment you click this, the corresponding JSON file with your user ID and credentials gets downloaded, and that particular file has to be uploaded in the files directory. So essentially assume that this is your Google Colab notebook. Go to files and upload the JSON file. So once the Kaggle JSON file is in place, we can directly download the dataset into or import the dataset directly into our working environment. So as seen here, so this is the URL of this dataset. And as seen here, Nitesh FRE is the username and the corresponding dataset name. So all we have to provide is Kaggle datasets download and the corresponding URL. So once I select this, that particular dataset gets downloaded here. Let me quickly refresh. So as seen here, the chess image dataset GIF file has come in here, and let's quickly unzip it. And once unzipped, all the images corresponding to the 6 classes, for example, bishop, king, knight, pawn, queen, and rook, are imported into our working environment. So in this way, making use of the Kaggle JSON from the API which is downloaded from the user account, and once we have the URL of the corresponding dataset which we need, we can import the data directly. So coming back to our problem. So now let's build a neural network to which kind of trains on this particular data set to classify the images to one of these classes. So as seen here, we have totally 6 classes. So it's a multi-class image classification problem. So we're going to use Keras. So we are importing the required libraries. And once the required libraries are imported, so similar to any of the modeling exercise stated previously, we have to kind of split the data set into our training and validation data set. So Keras comes with an inbuilt function which goes by the name Preprocessing, where we specify the ratio of the validation and training split. As seen here, I had specified 0.2 as my validation split. So essentially in my data set, 20% of the data set is reserved for validation, where 80% of the data set is used for training. So it's a categorical labels. So the total data set which we have comprises of 552 images, out of which 442 are going to be used for training. So similarly, we have to specify the validation as well. So one set is for training and the other set is for validation. And out of the 552 files, 110 files are going to be used for validation. So let's quickly display a few of the sample images we have in place. So that's what this particular function I wrote here does. It kind of shows us the different images. For example, these are few of the images of rook, knight, king, etc. So essentially, we have imported the data from Kaggle into our working collab. And once we imported them, we're having having a look at the sample images. So then we are kind of looking at each of the size of the labels we have in the training data set as seen here. For different datas, we have, for example, 71 corresponds to the number of data points or images we have from Bishop in our training exercise. So once the data is kind of kept ready, or we prepared the data for the neural network to consume and get trained. So the next particular cell is the most important step, where we have the uh, actual the convolutional neural network built for the purpose of image classification. So as seen here, we have different terms like, as seen here, we are specifying the model as model Keras.sequential, and we are adding layers like convolution 2D, and we have some term called padding, activation, max pooling. So these are the key terms which go in building an image classifier using a neural network. So before actually going in depth in this particular piece of code, let me quickly show you what exactly a convolution neural network does in the backend. So this is essentially what a traditional convolution neural network looks like. So we have an input image. It goes through a series of feature learning. And finally, we have a softmax function, which kind of classifies to the different labels. So this is the image which goes in where the neural network kind of using convolutions picks the features. So from a systems perspective, each of the image which is coming in is nothing but a series of pixels. So what essentially the neural network does is it performs convolutions on this particular image. It goes through a series of convolution layers. Finally, it goes through a softmax activation function where we have the output. So let us quickly go through what exactly is happening in the convolution in the backend. So before going there, let's see the definition of convolution, which is picked up from Wiki. So it states that convolution is a mathematical operation on two functions, f and g, that produces a third function that expresses how the shape of one function is getting modified by the other. So this particular line is the key takeaway. So essentially convolution is nothing but where let's assume we have two functions f and g. It produces a third function which expresses how the shape of this particular f is getting modified because of g. So let me quickly show an example on what exactly these terms mean. So let's assume we have a grayscale image of pixels, which is a 4x4 matrix. Let's assume it's a grayscale image for the sake of simplicity. So a pixel value corresponding to 0 corresponds to a perfect black pixel. And if it's a 255, it corresponds to a perfect white. So this is the input data image pixel matrix which is coming in. So this is our function f in the definition of convolution. Then we have something called the filter. So filters essentially are used to identify the edges in a given image. So I strongly suggest you to read about Sobel filter post this lecture on what exactly it does. So let's assume we have a 3x3 filter. This is our function g in our convolution definition. So let's see how the shape of this particular input image, which is coming in as a 4x4, is getting modified because of this filter. So filter runs like a torch across this input image, and it kind of condenses into a much smaller form. So let's see how actually what actually happens. So let's assume the filter starts running over this particular input image. So essentially the first 9 values get picked up and it performs a dot product. So as seen here for this particular matrix, once we run it with the filter, this is the dot product value we have. Similarly, for the next 9 values in the input image size. Similarly, the third one, and finally the fourth one. So in this way, we run a filter across the input image, perform a convolution, and this is the output condensed form we have. So this is essentially what a convolution is happening in the backend. And there's something called padding exercise. So what exactly is padding? So as seen here, from a 4x4 matrix of an input image, after running the filter, we got an output of 2x2. what if the user wants to retain the same size of the input image to the corresponding output which is coming out after each convolution? So that's the padding exercise. Essentially what padding exercise does is just adding zeros across the matrix. So this 4 cross 4 matrix of the input image, the moment we convert it into a 6 cross 6 by adding additional zeros, we are going to have a 4 cross 4 output. That's essentially is our padding exercise. So what exactly is max pooling? Well, going back to the previous statement I had mentioned, let's assume there is an image where we have a sky and a tall building, just two objects. So the assumption is all the pixels corresponding to the sky tend to have similar values, whereas the image of the building, assuming it's a different color of that of the sky, the pixel values are going to be different. So what max pooling does is once we have multiple output we have after each convolution, using the max pooling layer, we kind of pick. Let's assume that the max pooling we're applying for 2 cross 2. So for every 2 cross 2 values, it'll pick the maximum value and gives us the more condensed form. So this is essentially what we are trying to do. So we have an input image. It goes through a series of convolutions by making use of a filter and finally applying a max pooling layer on top of that. So now let's jump into the image where we've seen previously. So as seen here, we have a convolution, then it goes through the pooling layer. Then we have the next convolution, we have the next pooling layer. So in this way, we can build a series of convolution and pooling layers before actually flattening it out. So what happens in this flattened layer is each of the class labels which we they have a corresponding value of probability. So let's assume for this particular input image, it looks like a car. So my assumption would be like if the model is really well trained, the car will have the highest probability. Let's assume the probability is 0.7. The remaining probability of 0.3 is split across the different other classes which are available. So so when I give this particular image for testing for this fully connected neural network, the output or the label which is going to be predicted is going to be car. So this is essentially what the convolutional neural network does in the backend. Now let's quickly jump into the code. So here we have built a 3-layered neural network where the number of convolutions in each layers are 32, 64, and 128. So I kept the padding and the activation is ReLU unit. And once all the 3 layers are connected, we are flattening it out and preparing the model. So let's see what the model summary is. It's a sequential model with fully connected multiple layers of convolutions, essentially 3 layers and flattened out. And next we are going to specify whether it's a single class classification problem or a multi-class classification problem. So the loss we are specifying as categorical cross-entropy. This is essentially the requirement when it's a multi-class classification problem. And the number of epochs we have set is 8. The moment we fit on the training data, for each of the epochs as seen, the accuracy is increasing on a step-by-step basis. For example, for the first epoch, the accuracy is 0.19. And towards the end of the 8th epoch, we have close to 0.35. So let's quickly plot the accuracy for the training and validation data sets. And as seen here, for the training data set, the epoch, as the number of epochs is increasing, the accuracy is increasing. However, that's not the case with respect to our validation. So the reason may be we had tried to overfit the data because number of, as seen from the training data set, the accuracy is increasing as the epochs are increasing. So maybe we can reduce one of the convolution layer and try out with 2 convolution layer and see what the output is. And as seen the validation, the epochs, the accuracy is going for a toss. Maybe one of the reason being the raw data set which we had, the size is small. We can have more number of images for training the data. And once we have this training and validation data set, we can even have a look at the confusion metrics which I had built. So as seen here, the most of the bishops are getting classified as pawns. So the performance of the model is not really that great. As mentioned earlier, the reason may be one, we had overfit the data on the training data set, or the data set is not really huge for the model to get trained. So this is how we make use of Keras to build a convolutional neural network to build an image classifier. In continuation, in the next lecture, we'll be seeing how we can make use of Google Cloud Platform to solve the same problem with their out-of-the-box solution, which goes by the name AutoML Vision. Thank you.